Okay, good afternoon, everybody, depending on where you are. It could be good morning as well. As Timo said, my name is Simon Bennett, and I'm going to just talk you through some of the elements that we describe in chapter 1 of the report mostly. So it's sort of the framing for the report. And Timo already mentioned that one of the key elements of the framing was this request from Japan to provide input into the G20 presidency. But this is not the only impetus for the IEA enhancing its work on hydrogen and producing a report at this time. There is clearly, and I'm sure that everybody on the line will recognize this, an unprecedented momentum behind hydrogen currently around the world. And so this is the first point that I think it's worth starting with in this slide. We are able to chronicle more and more policies, projects and plans by governments and companies around the world. And when we talk about companies in this context, the breadth of the interest is quite remarkable, from renewable electricity suppliers to industrial gas producers, electricity and gas utilities, automakers, oil and gas companies, major engineering firms. And when we look at governments, we're talking about those who import energy, those who export energy, and municipal governments and cities as well. So, you know, in the report, we have looked at some of the previous sort of what you might call hype cycles for hydrogen, and we document 3 of those that have ended in relative sort of disappointment in terms of the scale of takeoff of hydrogen. And we think that one of the reasons why things look different today is this kind of breadth of stakeholder interest. And in the work on the report, we tried to have a look at what might be behind this, what might be kind of creating the not only the interest but also the investments that we're seeing around the world. And I think that the key issue is that hydrogen actually can help overcome many difficult energy challenges, but some of those challenges are things that have really emerged onto the energy policy scene much more strongly in the last decade. So taking 3 of these in turn, the first is that hydrogen has the potential to integrate greater amounts of solar photovoltaics and wind, whose availability is not always well matched with demand. So hydrogen looks to be one of the most cost-effective options for storing electricity over days, weeks, and months. Perhaps it already is the lowest cost option for some of these applications, and it's potentially our best solution to interseasonal storage. So as the expectations for renewable deployment have increased with the falling costs of renewables, people are looking much more strongly at hydrogen in particular. And we see hydrogen playing a role in flexible power as well in the power system in a way that can back up renewable electricity. So the second aspect is that in the last just 5 years or so, especially with the signing of the Paris Agreement, many more governments and stakeholders around the world are looking at much sort of deeper decarbonization pathways and how to really get carbon dioxide emissions out of the energy system. And in that regard, the options for decarbonizing steel, chemicals, freight and long distance transport, including via ships and planes, has really come onto the agenda, and people are looking for the best and most competitive options in the future for low carbon fuels. And hydrogen in each of these sectors is one of the leading candidates. So that's put it on the agenda, and that's again strengthened the stakeholder community around it. And thirdly, I think there is, at the IEA, it's incumbent upon us to stress the importance of energy security, both through diversification of the fuel mix, but also trade. And in a low carbon society that people are planning for today, hydrogen clearly adds something in terms of its ability to be made from many different energy sources, in fact, all energy sources, and to provide as an energy carrier, a chemical energy carrier, to provide energy flexibly to many, many different applications. So these are 3 kind of key changes that we see in the energy policy debate that are strengthening the optimism around hydrogen. But we should not forget that there are challenges which persist in this sector. We've mentioned 4 of them here on this slide, and each of them are things that we're going to touch on as we proceed through the presentation today. One is that hydrogen, especially from low carbon sources, remains expensive. Costs need to come down. The second is the tension that persists, especially in the transport sector, between the development of infrastructure and the investments that need to take place in end-use applications or hydrogen supply. And the coordination challenge of infrastructure is something that provides risks. Today, most hydrogen is from fossil fuels. That's something we're going to come on to in a moment. And we need cleaner hydrogen. And lastly, there are, in many cases, regulatory barriers or barriers in terms of absence of standardization, which are making it harder for people to make investments in this sector. So that's kind of the framing of the work that we've been doing in this report. And in order to then get a handle on some of these issues and how they are changing, we developed what we think are three unique databases for this work. And the first of those is a database on policy support. So we undertook a survey with the support of the Hydrogen Technology Collaboration Program that we manage here at the IEA. And we asked for governments, and we surveyed governments in terms of which policies they already have in place, in terms of targets, in terms of direct incentives that support investments in hydrogen. And we found that there's a growing number of countries that have policies in place to encourage hydrogen deployment. And actually, by mid-2019, the total number around the world is around 50 policies in place. So it's higher than at any time previously, and that's natural, but it's reaching a level that is really sort of a tipping point in terms of encouraging action. Among the G20 countries and the European Union, 11 countries have policies in place and 9 have national roadmaps for hydrogen energy. And that's a data set of policies that we've made available for free on our website now, and we encourage people to go and download that at the end of this webinar, ideally, and also to provide us feedback if you have any suggestions for additions to that. There's a second database that we've made freely available on projects for the supply of low carbon hydrogen around the world, and we've got some charts on that you'll be able to find in the report, and we encourage you to look at that as well. But I'm going to talk briefly about the third data set that we have in place now, and it's actually on the supply of hydrogen throughout the energy system since 1975. So in order to understand the growth of hydrogen and where we stand today in terms of its production, so where it's being produced, from which fuels, and the sectors in which it's being used around the world, we've tried to go right back to 1975 and look at energy data, industrial data, to make these to build up a data set and to show growth. And what we found is that since 1975, demand for hydrogen has been growing at around 3% per year. That might not sound like a great deal, but what it means, if you look at this, the chart, is that demand for pure hydrogen around the world has grown 4 times in over that period. And when we talk about pure hydrogen, what we mean is the use of hydrogen that is what you might call molecular hydrogen in a pure form, so not mixed with anything else. And the demand for that hydrogen is mostly today in the refining sector, where it's used for hydrotreating and hydrocracking of oil in order to produce transport fuels in the main, but it's also used in the chemical sector, and the main use there is for making ammonia, and most ammonia today is used in fertilizers, expanding food production around the world, which has had a huge impact on our ability to feed the world over those decades. So what we found is that in total, the demand for pure hydrogen has reached around just over 70 million tons, and that is a significant amount of demand for hydrogen. It proves the hydrogen is already with us, and that it's already with us at a really quite a significant industrial scale. Just to put that into context, that is enough hydrogen to power 500 million vehicles on the road, so cars, and that's half of the cars that are on the road today all around the world. So when we're talking about expanding hydrogen and making it a part of our energy system, it is worth reflecting on the fact that it already is something that is handled in industrial forms globally in very large quantities. We also put together a parallel data set on the demand for hydrogen, the use of hydrogen, mixed together with other gases, because this is a slightly more complicated picture, but it's also important. And what we mean there is that certain sectors, they use hydrogen, they produce hydrogen, but they don't separate it out from the other gases that are produced at the same time. And in most of the cases, that's carbon monoxide. But that hydrogen is used in methanol, it's used in steel making through the direct reduction of iron, and in some other applications as well. And just like with the pure hydrogen, most of that is coming from fossil fuels today. And it's the impact of that production, that current industry for producing and using hydrogen on our environment, is something that we're going to turn to in the next slides.
Yeah, thank you very much. So my name is Uwe. I would talk a bit about production and transport of hydrogen. So as Simon just mentioned, the production of hydrogen today is largely based on fossil fuels, dominated by gas, but also coal, particularly if you look at China today. And this leads globally to CO2 emissions of around 830 million tons of CO2 per year. Just to put this number into perspective, that corresponds to the annual CO2 emissions of the UK and Indonesia combined today, or represents a quarter of the CO2 emissions from cars that are on the road today worldwide. It is quite understandable, or the reason why it's based on fossil fuel, I guess, is not surprising. It's really basically just economics of producing hydrogen from fossil fuels. It stays still, in most cases, the cheapest option. In most parts, it's actually natural gas, the cheapest option to produce hydrogen. And this can be, or natural gas can also be coupled with CCUS, so meaning that the generated CO2 is captured before it reaches the atmosphere. That can either be then stored underground, or it can also be used in, for example, for enhanced oil recovery. If one looks at the costs of coal, it's actually also quite cheap. As I mentioned before, that's largely occurring today in China. The other option to produce hydrogen is to use electricity and water, and then using electrolyzers to produce hydrogen and oxygen as a byproduct. That's actually today the most expensive or more expensive option, and scale-up is really required to bring down the costs of water electrolyzers in the decades or the years to come. Scale-up of CCUS for hydrogen production has already begun. This is illustrated or based on significant efforts of government industry over the last 2 decades all around the world to deploy or deploy more or introduce CCUS into the energy sector. If we look at hydrogen production, there are today already 7 projects that are linked to CO2 capture. As I said before, otherwise it would be CO2 that would be emitted to the atmosphere. Generally, the CO2 is stored underground. As part of its use, it can also be used for enhanced oil recovery. In other cases, also may be used or sold commercially and then used for industrial purposes. Even if the number of current projects of 7, what I mentioned before, appears quite low, the hydrogen that's actually produced from these CCUS facilities today is more than 20 times the hydrogen production today from water electrolyzers around the world. So that we identified in our database around 200 projects of electrolyzers, and again, CCUS for hydrogen from CCS production is actually larger than the hydrogen from electrolyzers. And actually more CCS projects are underway. We identified 15 projects around the world that are in construction, so have been announced. Of these, 8 CCS projects were announced last year in Europe, and all were for the application of CCUS to hydrogen production at a large scale. The other option for CCUS also is to apply it to existing hydrogen production facilities. There we're talking mainly about refineries or the chemical industry. So that's another opportunity for CCUS to clean up the existing production pathways for hydrogen, as I said before, as we've seen before, it's largely linked to gas production, or in the case of China, also production of hydrogen from coal. And so retrofitting these existing facilities is a further option to clean up the existing production of hydrogen from fossil fuels. I mentioned the word scale-up already a few times. So scale-up is also happening for hydrogen production from renewable electricity. Over 200 projects have we identified that have started operations since 2000 around the world. And the encouraging news is they're actually getting bigger over years. So projects have been announced today at a size up to 100 or 200 megawatt of electricity input, compared to an average of around 1 megawatt over the last decade. But also has to keep in mind that these projects are still relying on government funding. They need to scale up and they need to become commercially viable to further bring down the costs of hydrogen from water electrolyzers in the future. If so, or if this is happening, we can see some remarkable opportunities for hydrogen production from electricity around the world. So what you see here on the map is analysis where we tried, or where we analyzed every square of the Earth at a half a degree resolution and optimized the combinations of solar and wind that would give the lowest cost of hydrogen production. So what you see here on the map is the generation cost of hydrogen from dedicated plants of, or combination of plants of solar PV and wind. And you can see here that costs in some parts of the world can be at $2 per kilogram of hydrogen or even lower. And just to put that number into perspective, for gasoline in the US, we're currently paying the same price of $2 for the same energy amount, which is roughly 1 kilogram of hydrogen roughly corresponds to 1 gallon of gasoline. If you look at Japan, the same amount of gasoline would be a bit more expensive, so they'd be talking about $3 for an energy amount, again, equivalent to 1 kilogram of hydrogen. Comparing with other production routes, so we've seen before the production costs of natural gas, for example, there we're talking about costs of around $1 to $2 per kilogram. So that shows that hydrogen from renewables can become competitive even with fossil fuels in the future. But as I mentioned before, scale up of the production chain for electrolyzers is critical to bring down the capital related costs of hydrogen production from electrolyzers. Further, what we can see on the map is the disparity on costs between regions. That's also illustrated, kind of hints to the opportunity for trade of hydrogen between world regions. Some countries will have the opportunity to export renewable energy in the form of hydrogen in a low carbon world in the future. And hydrogen or hydrogen-based fuels can transport energy from renewables then over long distances from regions with abundant renewable resources of solar PV and wind, for example. If you look at Chile, Northern Africa, or Australia, for example, on the map here, so they could kind of benefit or become renewable energy exporters in the future, and then deliver this hydrogen to regions that are dependent on, or likely to be dependent on clean energy imports in the future, for example, like Japan. Having a closer look at the hydrogen production costs from electrolyzers, two cost components are relevant. I've already mentioned the electrolyzer and the capital costs for the electrolyzers, but it's also the second cost component is actually the cost of electricity. And looking at particular hydrogen production from grid electricity, so this line shows you price duration curve for grid electricity. In this case, it's an example taken from Japan, and electricity prices, not surprisingly, are low when there's little demand, or even zero negative prices when there's surplus of renewables. So that as these low electricity prices, however, occur only for a few hundred hours throughout the year, so that the capex part of this loss, or the capex part of these costs for hydrogen production would be still quite high. In contrast, a high number of full-out hours will lead to a lower capex part of the hydrogen production cost. At the same time, also the costs of electricity are increasing because we are entering an hour when there's higher electricity demand, leading also to higher electricity costs, so that overall electricity becomes, if you move to higher full-out hours, becomes again more expensive, and also hydrogen becomes more expensive. So actually there's kind of optimum or sweet spot for hydrogen production from electricity, which lies around in a range depending on the electricity system and country or region. One is looking at between 2,500 and 6,000 hours per year. Overall, whether we talk about grid electricity or dedicated renewable electricity generation, combination of low electricity costs and sufficiently high full-load hours is needed to really get an optimum or get low hydrogen costs from water electrolyzers. That's a kind of challenge. So it's not only having low electricity costs, but also keeping an eye on the achievable full-load hours. So this combination of low electricity costs and sufficiently high full-load hours is a kind of recipe for achieving low hydrogen production costs from water electrolyzers. For hydrogen to be a fuel or feedstock in a clean energy system, the question is also important: what are the associated emissions with producing hydrogen? If you look at the production of hydrogen from coal, it actually leads to CO2 emissions of around 20 kilograms of CO2 per kilogram of hydrogen. And this means, if one just to put the number in perspective, is currently, if all the current production that you've seen before of 700 megatons of hydrogen would be produced today from coal, it would lead to CO2 emissions of 1.4 gigatons of CO2, which is roughly equivalent to the today's combined emissions of Japan and Australia combined. Carbon footprint of hydrogen from coal can be drastically reduced by combining it with CCUS, so leaving CO2 emissions of around 2 kilograms of CO2 per kilogram of hydrogen. If we look at gas, that actually leads to lower CO2 emissions than coal, which is not surprising, of around 10 kilograms of CO2 per kilogram of hydrogen. And again, combining hydrogen production from gas with CCUS could reduce CO2 emissions compared to coal by 95%. If you look at water electrolyzers, the other CO2 emissions is very much linked to the carbon intensity of the used electricity. So if you look today at the global average CO2 intensity of 500 grams per kilowatt hour of CO2, that would actually lead to higher CO2 emissions compared to the two fossil fuel pathways, whether it's coal or natural gas. So there it's also important that the electricity being used for electrolyzers is also sufficiently low carbon intensity. If we would use electricity from gas-fired power generation, that would still lead to higher CO2 emissions compared to the case where we directly used natural gas due to additional conversion losses. So that's really not surprising that we end up with higher CO2 emissions in this case. Actually, if one would actually the kind of CO2 threshold, CO2 intensity threshold to make water electrolyzers, the CO2 intensity of water electrolyzers comparable to natural gas, they would need a CO2 intensity of around 185 kilograms of CO2. That illustrates again that for water electrolyzers to become a clean a clean hydrogen source, the CO2 intensity of electricity has to be sufficiently low. Ideally, in the case of renewables, it would be close to zero, so that would be the lowest option for producing in terms of CO2, the lowest CO2 intensive option to produce hydrogen. So far, I only talked about the production or the production cost of hydrogen. But if we talk about the delivered cost of hydrogen, it's also important to keep in mind the cost of transporting hydrogen, especially keeping in mind that the energy density of hydrogen is quite low. So it's really a challenge in terms of transporting, storing, and distributing hydrogen. It really raises the question: what's the best way to do this? There are different possibilities available to transport, to address the transport channels. Like natural gas, hydrogen can be liquefied at temperatures of minus 250 degrees Celsius to increase its density. This requires, however, based on today's technologies, around 20 to 35% of the initial hydrogen to be liquefied. Just for comparison, for natural gas, this energy penalty is around 10% today. An alternative option is to incorporate the hydrogen into larger molecules that can be more readily transported as liquids. For example, ammonia is here an option. There, the conversion losses would be around 70 to 18%. The third option that we've analyzed is to use so-called liquid organic hydrogen carriers. So there, hydrogen is loaded into molecules such as toluene, and then this toluene has very similar properties like a liquid, can be transported. And so we look at these three options as you see here. If you look at pipeline transport for domestic or for inland transmission of hydrogen, there the cheaper option for distances below 3,500 kilometers would be natural gas. Above that, ammonia would be the cheaper option. If you also take into account shipping, which is shown on the right graph, the transport of liquefied hydrogen using pipelines is cheaper for distances below 1,500 kilometers. Above this distance, we see that ammonia, but also liquid organic hydrogen carriers are the cheapest option. The cost difference there, at least to our assessment so far, which still has also acknowledged that there are quite some uncertainties, particularly on the future cost of LHC, is a cheaper option. So that again, for long distance shipping, ammonia and toluene appear to be the most promising options. Having said that, cost is not the only criteria to consider, particularly if we look at ammonia, but also toluene. These are toxic substances, so they will also keep in mind to ensure that these chemicals or carriers are properly handled, and also that way avoid any adverse impacts on the environment. So having talked about production and transport of hydrogen, my colleague Peter will talk now a little bit more in the uses of hydrogen that we've analyzed in this report. So please, Peter.
Thanks, Uwe. So as we saw at the beginning of this presentation, today hydrogen is mainly used in the oil refining and chemical industries. But for hydrogen to make a significant contribution to the clean energy transition that we need to undergo, it also needs to spread to be used in other sectors. This gives us two main categories of opportunities over the next decade. So firstly, hydrogen demand in existing industries is growing. All of these uses can readily accept substantial quantities of clean hydrogen instead of hydrogen generated from unabated fossil fuels. And we can get to very high scales very quickly just by deploying CCUS and electrolysis for these sectors, which will bring down the costs of hydrogen production significantly over the next decades. In the last 12 months, there have been announcements from some of the world's largest refiners, fertilizer manufacturers, and steel makers, notably in Europe and Australia, and these companies plan to build electrolyzers to supply hydrogen to reduce their emissions. And then the second category are new uses for hydrogen, and we're starting from a much lower level of demand here, but there are ambitious plans that have been set in place around the world. For example, in the building sector, it's already been shown that hydrogen can be, it's already been talked about a lot, that hydrogen can be blended into the natural gas grid and used safely in homes. But now projects in Europe and Canada are aiming for a significant scale up in this area. And if you add up the ambitions of these projects around the world, these proposed plans, they look to supply about 4 million homes worth of hydrogen by 2030. And then in the cars and vehicle segment more generally, there are 11,200 fuel cell cars on the road today. But just looking at official government's targets, this would increase the vehicle component to 2.5 million by 2030 if all these plans were realized. And then there are a couple of other sectors where we think hydrogen will be particularly important in the long term, but where it hasn't made much of a dent in the market yet. So clean hydrogen converted to liquid fuels or ammonia, like Uwe was touching on before, using technologies that are well known today. These are among the most promising options for cleaning up shipping and aviation. But they'll take some time to develop, and we need to start on this now. So let's first take a look at the existing sources of demand that we see growing in the period to 2030 and beyond, with the chemical sector being the largest among these. The two most important bulk chemicals from a hydrogen demand perspective are ammonia and methanol. And these charts show how we expect demand for hydrogen for these chemicals to evolve under a projection of current trends. So demand for ammonia for existing applications is set to increase by around 1.7% per year between 2018 and 2030 and continue to rise thereafter. This rate of growth would mean around 38 million tons of hydrogen demand for ammonia production by 2030, relative to around 31 million tons today. For methanol, demand for existing applications is set to grow at around 3.6% per year between 2018 and 2030, so faster than ammonia. And the methanol to olefins and methanol to aromatics segment of this is expected to grow even faster. And this is a chemical technology that allows you to produce plastics and other materials from, say, coal feedstock, which is commonplace in China today. And this rate of growth would mean 19 million tons of hydrogen demand for methanol by 2030, relative to around 12 million tons today. So quite fast growth in the methanol segment. And there are some other sectors which I won't have time to go into here, existing uses. We expect nearly 3 million tons of demand growth from the refining sector and around 4 million tons from the iron and steel sector in the direct reduced iron route that was mentioned at the beginning. So again, sticking with the chemical sector, let's take a look at the economics of production via various process routes. Fossil fuels have long been a convenient source of and a cost-effective source of both the hydrogen and, in methanol's case, the hydrogen and the carbon that's required for feedstock for these chemicals. In 2018, around 270 million tons of oil equivalent of mainly gas and coal were used to produce the hydrogen for these two products. Roughly equivalent, this quantity is roughly equivalent to the combined oil demand of Brazil and Russia. Gas is the dominant feedstock for ammonia and methanol globally, with China and small shares of production elsewhere utilizing coal. So taking a look at ammonia specifically, we can see considerable variance in costs for the production based on both coal and natural gas. In regions with high natural gas prices, such as Japan, the levelized cost of ammonia production can be more than $500 per ton, whereas in those with access to low-cost gas reserves, such as the Middle East, levelized production costs can be less than half this figure. These existing pathways can be equipped with CCUS, as shown in the middle of the chart, either in greenfield projects, as we're showing here, or via retrofits. CCUS offers the potential to dramatically reduce CO2 emissions by 90 to 95% without large increases in costs. Then the electrolysis pathway and biomass gasification, which is not shown here for clarity, these routes offer the potential to eliminate CO2 emissions altogether on a net direct basis, with the caveats that the CO2 intensity of the electricity, as Uwe outlined, has to be below a certain level to get to an emissions benefit, and the sustainability of the biomass in the biomass gasification case has to also be a factor to consider. So in regions with the best renewable resources, providing electricity at a cost of between $15 and $50 per megawatt hour, we estimate that the electrolysis pathway could be competitive with fossil fuels in several regions. A similar story to what has been presented here for ammonia is also true for the equivalent process arrangements for methanol. So besides existing industrial uses, of which the chemical sector was a partial summary, hydrogen has also got the potential to grow in new applications. And I want to highlight just two in this presentation, as we don't have a lot of time, but please dig into the report where we examine several others. So firstly, trucks. While there are around 11,200 hydrogen cars on the road today, there are only around 400 trucks and around 500 buses. Not only did trucks consume much more hydrogen than cars over their lifetime, but they also tend to concentrate their journeys in so-called corridors, traversing specific highways to and from ports and industrial hubs and along these corridors. And these are the main reasons why we identify them as a key new application. And just to take a look here at the future economics. So we're using the total cost of ownership metric here. And if hydrogen fuel cells were to reach a cost of $95 per kilowatt, and battery costs were to decline to $100 per kilowatt hour, the battery and fuel cell trucks we examine here could have a similar cost, assuming a driving range of 500 kilometers. One of the critical variables to achieve this competitiveness is to ensure that the hydrogen being used is of low cost. This includes low production and distribution costs that Uwe has covered. in the previous slides, but also a low cost for the refueling step. So this in turn requires a high degree of utilization of the refueling stations to ensure that the capex, which can be in the order of $1.5 to $2 million for a station, only accounts for a small share of the overall hydrogen delivery cost. And of course, an alternative to this, to achieving this high utilization, is more of a hub and spoke model rather than refueling stations along the corridor, where a dedicated fleet can operate on fixed routes and then refuel at a single centralized station. And now lastly, just to move on to the second example of new applications, heating demand in the building sector. While there's much talk of blending some proportion of hydrogen into existing natural gas supplies, here we examine the near-term potential and the economics of a pure hydrogen supply, similar to projects that are being discussed in the UK at the moment. So we find that hydrogen used for heating in buildings presents a substantial outlet for growth, but the economics of this will be critical. So delivered hydrogen prices to consumers would need to be in the range of $1.5 to $3 per kilogram of hydrogen, to compete with natural gas boilers and electric heat pumps on an already installed basis, so excluding the capex component. For certain countries like Canada and the US, where lots of cheap gas is available, the hydrogen prices would have to be even lower, so around $1 per kilogram of hydrogen. If this level of cost decline were to be achieved on the supply side, though, the market potential in buildings is very large, in the range of 12 to 20 million tons of additional hydrogen demand by 2030. This estimate takes into account the stock turnover of natural gas boilers and these natural gas price competition elements that I mentioned with the boilers and heat pumps. Serious planning, though, would need to be undertaken today for the necessary deployment to be, for the potential identified here to be achieved by 2030. And it would also be imperative to overcome concerns relating to safety of handling and distributing hydrogen in residential areas. So at this point, I'd like to hand back to Simon to talk about value chains.
Thanks, Peter. And I hope that the previous descriptions of the work in the report were not too high level for everybody. I'm sure that you all have interests on the specific sectors and the specific topics. But what we've tried to do in this presentation and in the report more generally is to provide a solid overview of the status of hydrogen today, its key areas of future potential, and some of the issues and challenges that it faces. And the reason why we've aimed to make this accessible in the way that we have is because this is a specific request from policymakers who are looking for more information to understand what some of the roles are for hydrogen as compared to other energy options. And it was incumbent upon us to then move the discussion away from just the sector by sector description, some of the work that Peter just presented, and towards what could be solid policy messages that we could provide to help governments understand where to move next. And the way that we've ended up framing some of our policy recommendations is around what we've called 4 key opportunities for scaling up hydrogen. And throughout the report, we focus on 3 time horizons: today, 2030, and the long term, broadly mid-century. And we see 2030, the reason why we've highlighted this, as a critical moment for hydrogen in its deployment journey. We think that getting to 2030 with what we call a springboard for future hydrogen deployment established, and that means bringing down costs, scaling up supply technologies, developing essentially an industry that can be making sustainable investments on the basis of confidence in future revenues, is the key challenge for governments and industry in the next 10 years. And looking at where the risks lie and all the challenges in the various different sectors, we've tried to find these 4 opportunities based largely on where there are existing infrastructure, so that there isn't the coordination problem of developing new infrastructure and the challenge of developing new sources of demand and investments in new equipment that's going to be using the hydrogen, all at the same time as developing low carbon hydrogen supply, and also building on existing government policies and targets. So quickly going through the four as they appear on the map here. The first is industrial hubs, and we see that a great opportunity to make industrial ports the nerve centers for scaling up the use of clean hydrogen over the next decade. So much of the refining chemicals production that uses hydrogen today and uses hydrogen that is based on fossil fuels is actually already concentrated in coastal industrial zones around the world, and these include the North Sea in Europe, the Gulf Coast in North America, and Southeast China as well. And there's a real opportunity to encourage these plants to begin to shift to cleaner hydrogen production and use. And there is no need in those situations to develop new infrastructure for using that hydrogen. Those industries have the protocols in place for the safe use of hydrogen and can use hydrogen at scale. But what it would do is it would scale up hydrogen production, whether that's from electrolysis or CCS, and would drive down costs. And by being at locations near ports, these hubs are great connecting nodes between the inland use of hydrogen, potentially via pipelines, and also getting hydrogen use on ships and hydrogen trade facilitated. And when I mention pipelines, that brings me on to the next opportunity that we see, which is talked about, especially in Europe at the moment, around the use of hydrogen in gas grids. And there hasn't been time to go into this in a huge amount of detail. It is related to the story of use in buildings heat that Peter was just describing. But there's an opportunity to blend hydrogen at low volumes into the gas grid without, again, needing much new infrastructure, much new investments in end-use equipment, and also an opportunity to begin exploring how some existing pipelines, making use of existing infrastructure and existing capacity and skills around the world, could convert those the existing pipelines to 100% hydrogen use. Because in the long term, a very long-term low carbon, perhaps net zero carbon goal would mean that the whole gas supply in particular regions would need to be decarbonized. And we need to start looking at technologies and opportunities for that. And this has been proven in a number of projects around the world. And actually we see some of the biggest projects that are on the table today looking for investment are specifically aiming to inject hydrogen into the gas grid. The third is mobility. When we look at the targets that governments have around the world to raise the number of, for example, fuel cell vehicles from the 11,200 that we have today, the targets are fairly phenomenal and they're growing. So in China, there's a target for having 1 million vehicles on the road, the same in California. Japan and Korea, so 600,000, 800,000 each by 2030. These are ambitious targets, but we think that they are achievable, and that would add nearly 1 million tons of hydrogen demand, and it would help to scale up the infrastructure that is needed if there is a scale up that maximizes the use of the refueling infrastructure. I think that's the key point with mobility policies relating to hydrogen. And the opportunities to maximize use of refueling infrastructure are related to what we call freight fleets and corridors. That's easy for me to say. And we're talking there about trucks and long distance vehicles. We're also talking about taxis and perhaps some key opportunities to move goods, so between nodes at ports and other deliveries where there are air pollution concerns around some of the cities in those locations. So that's mobility. The final key opportunity is around international trade. And while we're, the 2030 time horizon is about getting the first ships that carry hydrogen, that ship low carbon energy between regions that have disparities in terms of their resource endowment. The reason why we're calling this a 2030 priority is that when we look at the LNG market, it clearly took many decades to scale up to the point where it is today. Today, it's around 3% of global primary energy supply. In order to get to something similar for hydrogen, we need to accelerate that deployment, and it will take international cooperation and concerted efforts, both in the private sector and the public sector, to facilitate those investments, both in supply and demand for hydrogen. And so action needs to start now. And I think that that picture of those four key opportunities, the common thread, apart from building on existing infrastructures, that we need to start now. The decade to come is going to be a crucial time, and there is great opportunities for cooperation. And that's also a thread that runs through the 7 key policy recommendations that we've included in the report, and with which I'm going to conclude our presentation today. So putting them all up on the screen here and quickly talking through them, they are fleshed out in much more detail in the report, but I'll mention a couple that haven't been touched on so far. And the first one I think is critically important, and it's to establish a role for hydrogen in long-term energy strategies. So this is not about just coming up with a hydrogen-specific policy, whether it's in a government or whether it's a corporate strategy. It's about how does that fit into the overall expectations for the evolution of the energy system and the key policy targets that different countries will have. And those policy targets will touch on air pollution, energy security, energy access, as well as climate change. But that long-term guidance is necessary to provide investor confidence. We've also highlighted the need to support R&D. I would say that this is not just about government funding for public R&D projects. The key thing here is that we need innovation, but we need innovation to be coming from all angles. And one of the key elements there is, alongside stimulating commercial demand for scaling up hydrogen, which will deliver economies of scale, it's about providing the supportive framework for the private sector to invest in research projects, demonstration projects in a coordinated way that begins to tackle some of the issues that we've raised in the report around the needs for fuel cell materials efficiency, for electrolyzer efficiency, especially if those electrolyzers are going to be run at low load factors, and a whole host of other great innovation opportunities besides, because let's not forget that the competitors to hydrogen across the energy system are also going to be improving, and there will also be innovation elsewhere. The recommendation number 6 is something that the IEA is particularly keen on, because we recognize that some of these things, especially international trade, but also standards around the world, standards for refueling stations, standards for safety. It's imperative that hydrogen is a fuel that's handled safely and handled well in order to bring the public along with the deployment of hydrogen. And there are opportunities to do that, in particular in an internationally cooperative way, and to not have hydrogen develop in silos in different countries. So we're really stressing that, but also the other element of that is at a global level, there's a thirst for accurate information on the state of play and the progress with hydrogen technologies. That's something that we've learned from our work on this. It's something that we've learned from governments and the corporate sector alike. And so there's a need to engage internationally on tracking progress as well. So our recommendation number 7, the final one, is just a reflection of those 4 key opportunities that I presented in the previous slide. And really, when we look at recommendations, especially 2 to 6, what we're talking about is looking at the context in different countries, looking at the context that faces different countries, the different choices that they will make, and seeing where they see their own situation reflected in those 4 key opportunities and identifying where they might act. We think that those 4 key opportunities are the main areas of action that we can envisage, but there may be others. We'll be very happy to expand those over time if folks tell us that we've only identified a subset of where the real action is going to be. The final thing that I will do before we bring the whole webinar to a close is just move on from our recommendations to mention the fact that the work on hydrogen at the IEA and around the world does not stop with one report. I think we are modest enough to recognize that much more needs to be done. And from the IEA side, we encourage people to look at our website, iea.org hydrogen, which will be continually updated with the latest information and where you can download data sets, as I said. And there's various other ways in which we'll be updating that with commentaries, but also something that may have passed people by was the Clean Energy Ministerial launched a new hydrogen initiative just last month and invited the IEA to be the coordinator of that initiative. And so stand by for more information on our website on that. But besides that, the things that we've learned in the production of the report will be fed into other IEA analysis such as the World Energy Outlook and our scenario work. In terms of analysis we think needs to be done elsewhere, we've highlighted a couple of things related to regional energy scenarios. What are the trade-offs at a local level? What are the opportunities? And how do we translate those scenarios into specific sectoral and regional policies and bring those sectors along with us in terms of making targets and strategies? And then for government and industry specifically, we just wanted to recognize that there's a need to prioritize policies that build upon dependable uses in industrial applications in particular, because this issue of the carbon footprint of current hydrogen use is something that has emerged as one of the key issues that we found in our work on hydrogen, but also stimulate new sources of demand. And there's a reason when we presented the 4 key opportunities that we used a cartoonish schematic that showed them all on one slide, and it's because they are connected, and all of these opportunities can work together synergistically. And finding those synergies is something that the government and industry can work together on. So that was a whirlwind tour of the report, and I'll conclude there and hand back to Timo.
So thank you very much to all of my colleagues here for the presentation. We went slightly longer than I was hoping for, but I think it just shows you that there's a lot of material in the report that I'd encourage you all to dig into. We received many questions in the meantime. We're not going to be able to address all of them, but I'm going to try to make a bit of a selection here with the colleagues on some of the questions that we hope are of interest to many more of you. Please don't hesitate, though, after the presentation to send us an email to hydrogen@iea.org if your particular question wasn't answered or if any further questions arise as you are studying our report. Let me first start with the most important question, is whether these slides will be shared. Yes, they will. We'll have recorded this webinar and we'll be making it available on our website, on YouTube, in fact, as well after this particular seminar. So most of the questions, if I may summarize that, deal one way or another, or many of them at least, deal one way or another with the assessment of hydrogen production. One of the key questions here is, in fact, in the slide about how clean is hydrogen, the question why carbon or why fossil fuels-based hydrogen without CCUS has a lower emissions intensity than hydrogen production from the global average electricity mix. And I would like to ask my colleague Uwe to quickly answer that question.
Yeah, it's probably, if one looks at the numbers, it's probably initially a surprising outcome. But I mean, if one does the math and based on the also the conversion losses of water electrolyzers around, let's say, 70%, if one takes 500 grams per kilowatt hour and one does the calculation, one ends up with the corresponding CO2 intensity. Again, it very much depends on what's the local circumstances in terms of CO2 intensity. So 500 grams is the average. As I said before, if one has CO2 intensity below 180 grams per kilowatt hour, one ends is on par with the CO2 intensity of natural gas without CCUS. So again, it really very much depends on the local circumstances. But keeping in mind that today, if we talk about grid electricity, so not dedicated renewable electricity generation, such a low electricity intensity below 180 grams per kilowatt hour is something only a few countries have, for example, as with high renewable share today already in generation mix, or high nuclear share like France, or in terms of nuclear, or for example, for the Nordic countries in terms of hydropower generation. So again, very much depends on the current generation mix. And again, it's probably initially surprising, but I mean, if one does the calculation, one ends up with these kind of intensities.
Thank you very much, Uwe. Another question right away on hydrogen production from renewables is, in fact, the question, isn't green hydrogen based on excess of renewable electricity a myth? Shouldn't green hydrogen production require dedicated production of renewable energy? And if so, are there signs this will happen anytime soon?
Here's also a very good question. I mean, If we talk about surplus electricity generation, that was also a bit what we talked about, the slide showing the generation cost from grid electricity, that these hours where when we've got surplus electricity, the hours that these electricity, surplus electricity available could be quite low. So we're talking about maybe a few hundred hours per year. And then the contribution, the capex contribution and the total hydro production costs becomes very high. So that's the kind of precondition. If you've got surplus electricity from renewables, they should be at sufficiently high full load hours. That doesn't mean that this situation cannot occur in practice. If I'm at some grid bottlenecks, for example, in Europe, there might be the situation that, let's say, for offshore wind, there's no grid access available. So there could be opportunities because of these mismatches in planning generation of renewables and also planning the grid. On the other hand, that situations might occur, but it could make sense for a certain amount of time to use water electrolyzers because the surplus electricity occur at sufficiently high number of hours in a year. The advantage of, let's say, water electrolyzers is that typically the electrolyzers are quite modular technology. So if these full load hours disappear, one can move the electrolyzer to use it somewhere else. So it could be a kind of transitional option if one really has the situation that surplus electricity occurs at high full load hours. But otherwise, I agree with the question or the comment that dedicated renewable electricity in the long term is probably the more promising option for water electrolyzers from renewables.
Thank you very much, Uwe. Moving on to the building sector. In fact, many of you remember that there was a slide where we showed the growth of hydrogen use to 2030, and there was a category new uses. The question is how much of this buildings category, which was arguably very big here, is due to the H21 North of England project? And I would like to ask Simon to pick that up.
Sure, thanks for the question. We clearly have a viewer who's both very well informed and paying attention. So the chart that we showed essentially what we think could be achievable in 2030 timeframe based on announced government policies, especially in the transport sector and targets in particular, and then elsewhere on announced projects that with a tailwind might be able to come online in the next 10 years based on their planning. And clearly in the building sector, there are two major projects that are announced, both in the UK, the H21 project and the HyNet project in Northwest England. And in fact, because those projects are dependent on relatively large scale, commercial scale, autothermal reforming of natural gas with CCS, they produce an amount of hydrogen if they were to come online, and we recognise that those are not government policy just yet. That would be much larger than all of the hydrogen needed for the vehicles targets. So yes, a lot of that is the H21 project. Some of it is the HyNet project, but those certainly represent the majority.
So next question is a bit of a question on understanding. It was dealing with the graph levelized cost of ammonia production in 2018, and the question was what we mean by the range in the legend. Peter?
Thanks, Timur, and thanks for the question. So the range here refers to the range of levelized cost that varies by region. So this is showing a snapshot of all regions across the world that we model in 2018, and the range is primarily being affected by the different fuel costs in different regions. So the lower end of this range is shown with the breakdown of the capex contribution, the opex contribution, the fuel and the feedstock, as well as the capture costs. So the breakdown is just for the lower end of the range, and then the overall range for the total cost is shown above that. We see multiple kind of factors and reasons why this range can be larger for different technologies. So for the electrolysis pathway, we're looking at a great variance of electricity prices. These would be grid signal prices at the moment that we see different prices in different regions. The cheapest prices that we see today are actually not, these would be from a generation mix that is not entirely renewables by any means. Even some of that price could have some fuel subsidies and other types of subsidies embedded within it. So this is why you see a large range, and then right up to a cost range of 150 euros per megawatt hour plus for the top of that range on the electrolysis pathway.
Thank you very much, Peter. Another one is, or there's a couple of questions, in fact, that are dealing with safety issues. What about safety? It was very much argued in early years. What's the current state of safety, etc., etc. Simon, could you say a few words about that?
Yeah, no problem to provide a brief overview of the topic, although it is quite a technical issue once you start to get into it. And in the report, we provide some details on some of the issues relating to the handling of hydrogen, its flammability, some of the issues relating to its potential for leakage as well. I think it's an issue that we're very much aware of, and especially in the light of the recent accident in Norway, where there was an explosion at a hydrogen refueling station, something that governments need to keep at the very top of their radars when looking at hydrogen in all of its different applications. Now, what we do know is that at an industrial scale in the chemical sector and the refining sector, hydrogen has been used for many, many decades, and protocols are in place for its safe use in relatively large quantities, in fact, just like the use of some of the energy products that we handle on a daily basis that have flammability or toxicity concerns. But certainly, as hydrogen is used in new applications and in new ways, safety should be something of paramount importance. And I think there's an opportunity around the world for the sharing of best practice to ensure that not only are accidents avoided, but that the public, as I said earlier, is brought along on this journey as an informed participant alongside the decision making of companies and governments.
All right. We have many more questions here that we have recorded, but we are running against our time limit here. I hope you understand. We'll bring this webinar to a close here, but as I said previously, we'll be happy to answer your questions if you just send them to us by email. hydrogen@iea.org is the place how you can reach us. With that, I would like to thank you all very much for your attention, for being around. We had at the peak a good 270 people at the on the record here during the webinar, which shows that there is really a great interest in the case of hydrogen. Encourage you to study the report and come back to us with questions if you have any. Thank you very much.